Hello, it's the start of a new set of videos on mechanics, and I'm going to start off with what you know from GCSE. So we're used to seeing these distance time graphs where we look at distance, speed and time, and we work out where we're going to be and what's going to happen. Okay, A level, we're going to extend what you know from that, and we're going to start looking at changing velocity, which is called acceleration, and we're also going to create new terms and new diagrams to help us with this. So first up, we're going to use this new term, displacement. So what's displacement? Well, displacement's like distance in our old diagrams, but we want to be very clear that it's a vector quantity. Yeah, so we can travel, in this case we started at the origin, we've traveled plus 40 meters in 10 seconds, then we've been stopped for 20 seconds, then we've traveled 60 meters in the opposite direction. Yeah, so displacement has clear direction. So at this point we're at plus 40 and down here we're at minus 20. Yeah, so displacement has direction as well as magnitude, and as a result it's a vector quantity, and we use the symbol S for displacement. So this is our fundamental measure for the future. It's a vector quantity of movement, and that's different from distance. Now distance is the scalar magnitude from displacement, so doesn't matter whether I'm plus 30 meters from you or minus 30 meters from you, I'm still 30 meters from you. So if I took the displacement graph we were just looking at, everything looks very similar at first, doesn't it? We traveled 40 meters away, and then we stayed there for 20 seconds, but then we traveled back until we came back to our original position. And then when we traveled negative 20 before, well, we're still 20 meters away, aren't we? We stay there for a period of time, and then we travel back to the origin. So what's the effect of this? Well, the distance. When in displacement we had negative values here. In distance, as we're only looking at the scalar magnitude, how far away were you? Well, they're going to be positive values, 20 meters here. Yeah. So that's distance for you. Now, occasionally we deal with, but not so often, distance travelled. Why would we be interested in distance travelled? Well, if I drive in my car to London and back, my overall, at the end of it, my overall displacement's 0, but I've still travelled 30 miles to London, 30 miles back, and I'll have used up the petrol for that. So I want to know how far I've actually travelled to work out what my fuel consumption is. So in this case, again, we're looking at some sort of distance. Here we've got distance travelled versus time, and the first part of our graph looks the same. We've travelled 40 meters in 10 seconds and we stood still, but at this point here we're travelling further, aren't we? We might be travelling back towards our start point, but we're still travelling further and using fuel. So we start at 40 meters of distance we've travelled, we then travel another 60, and we're going to add that on positively because that's all taking up fuel, isn't it? Then we stopped for 10 seconds and then we travelled another 20 meters. So there we are, we've now travelled 120 meters in our journey, and that's the fuel we would use up. So those are our three terms: displacement, distance was the scale of displacement, and occasionally we use distance travelled. Okay, at GCSE we often talked about speed, 30 miles an hour, 15 meters per second, something like that. Yeah, and we could see that from our lovely displacement time graph. Yeah, and we'd start measuring them off by looking at each of the elements. So let's have a look here. So we started at 0 at our initial position. We travelled 40 meters away in 10 seconds, and by looking at the gradient there, we could see that we were travelling at a speed of 4 meters a second. Now we're going to consider this in terms of what's that mean for velocity, because that was travelling away in a positive direction, so that's positive 4 meters, isn't it? Then we stopped for 20 seconds, and then we started travelling back. until we went past where we started and ended up 20 meters in the other direction. So if I look at the gradient of this, I'm actually got a negative gradient here. I've got minus 6 meters per second, yeah? And that's important because when we start talking about velocity, velocity again is a vector quantity, it has direction. So that's right, isn't it? We travelled, our velocity wasn't, if we were looking going forward, is +4 on this section here. We're actually going in the opposite direction here. We're going minus 6 meters a second. So we do that till we stop here. We're still here at 0 meters per second for a while. And then we travel back towards our start point at +2 meters per second. So what is velocity? Velocity is a vector quantity. It's the velocity, it's the vector quantity where speed is the magnitude. And it's the gradient from our displacement time graph. And it's also often referred to as the rate of change of displacement. So let's unpack that a bit. Well, displacement's how far we've travelled. Change, probably more straightforward because that's the change in it, how far we've travelled. But what's rate? Well, rate is effectively the per unit time part. So if we were travelling fast, our rate would be high. If we were travelling slowly, our rate would be low. 30 meters a second is faster than 10 meters per second. So the rate bit is per second. Okay, so we've just extended what we did with speed, and we now talk about velocity, which has a direction as well as magnitude. To help us with this, we quite often draw at A level velocity time graphs. So here's our axis, and now our green axis is velocity. We've still got time on the y-axis. And if we looked at the travel that we did in the last example, that's my yellow line here, that's my displacement. We've got this axis over here, yeah. That's my displacement time graph. I could draw a new red graph here of the velocity. So as we said, in the first 10 seconds we were traveling at +4 meters a second. Then there was a period of 20 seconds while we were stopped. Then we traveled at -6 meters a second. Then we were stopped again for 10 seconds. And then we traveled at +2 meters a second for 10 seconds. But this isn't very realistic, is it? Because we don't really suddenly go from 4 meters a second to 0 and then 0 to -6. That's not how the world works, is it? We have to speed up and slow down. And this speeding up and slowing down is called acceleration. And if those of you who drive a car, that's when you put your foot on the accelerator and it speeds you up, or you put your foot on the brake and that slows you down. So let's have a look at a graph, what a realistic graph would look like for a velocity time graph. Well, we start at 0 miles an hour, so meters per second, and we start accelerating. And we accelerate at 1 meter per second squared. Well, what does that mean? It means that after 10 seconds, we'll be doing 10 meters per second. We'll be at this point here, yeah? So we have 10 seconds where we accelerate and we get to 10 meters per second. We then travel along here at a steady speed, a steady velocity, yeah? So we're just carrying on at 10 meters a second till we get to here. After 50 seconds, we need to stop and get off our bike again, or stop our car. So what do we have to do? What most people would in vernacular call decelerate. Yeah, but until we stop. There we go, there's our stop point. In mechanics, we try and avoid using the term decelerate because acceleration is a vector quantity. What we actually start talking about is the fact that it's a negative acceleration. And we can see that because we can see our gradient on this section is negative. We can work out the gradient is -2 because we went from 10 meters per second to 0 over 5 seconds, didn't we? So 10 divided by 2, sorry, by 5 is 2. So during this phase, we have an acceleration of -2 meters per second squared. So let's just quickly summarize then. Acceleration therefore is speeding up, slowing down. We can find that from the gradient of our velocity time graph, and it is the rate of change of velocity. So we take our velocity, we change it, and we're interested in the rate of it, how much it's changing per second. So there we have it, and that's acceleration. We're going to do lots of work on acceleration. Okay, here's my quick summary of situation for you to stop the video, take an image of it, whatever you want at this point. And our key points are, we've got our new term displacement, S, each symbol S, which tells us what our position is, and it's a vector quantity, as opposed to distance, which is the scalar equivalent. We've got velocity, which is our vector quantity for movement or rate of change. And speed is the scalar quantity to go with that, and acceleration, which is the rate of change of velocity, so we can find that. And all these terms we can see from our two sorts of diagram. We've got our displacement time diagram from GCSE, and we've got our velocity time graph, which we're going to use at A level. So there you have it. Hope that's of use.